All right, hello. Today we're going to be talking about this specific sequential circuit called a Mealy machine. All right, so I'll go into detail about what this does, but before I do that, this is the circuit that I built based on the lesson that we are learning about. All right, and the difference that my circuit has compared to this one is that for the clock inputs here for these JK flip-flops, this circuit, the JK flip-flops are capturing the clock on the rising edge, where mine has these little circles here for the clock inputs, and that is making it so that is being captured on the falling edge of the clock. All right, so all right, let's talk about a sequence here where we can get our output Z equal to 1. All right, we have two state codes here, Q1 and Q0. There's only one case where we can get output to be equal to 1 here. So what we would want for that to happen is we would want our outputs Q1 and Q0 to be in state D. They're both equal to 1. So by cycling this clock here, I could get both of these flip-flops set equal to 1 here. Make sure that our input is set to 0. And then we should have this output here, Z, set to 1, and that's because our two state codes here, Q1 and Q0, are having an input of 1, 1 into this AND gate, as well as this X prime input here getting a 1 sent into it as well, gives our output of 1. And this is the only case where we'll get an output of 1 when all three are on. So what's cool about this input X here is that if you're cycling through any of these states, A, B, C, or D, what happens is when you turn this input on and then cycle so that it falls to the falling edge, our states immediately fall back to 0, 0, or the beginning state, which is A. So I could show you by going to, say, state C here, 1, 0, which is this state here that it's in right now. And I could just go ahead, hit 1, and then immediately go back to state A. And no matter how many times I cycle, it won't cycle through the states. It's always going to return to A. All right. So this is what makes this more of a Mealy machine rather than a Moore machine. What a Mealy machine is specifically is that the output is affected based on the present state or what the value is being stored in the machine. So like Q0 and Q1, as well as an input, right? But for a Moore, the output only changes based on the current states, Q1 and Q0, and does not depend on any inputs like we have up here. So for example, if this was to be a Moore machine, we would probably have to cycle through all states before being able to return to A. Whereas in this Mealy machine, we can cycle to any state and return back to the starting state just by having an input set to 1. All right, now let's take a look at the process of sequential circuit analysis. So here we have a given circuit, all right, and we can take a look at all these inputs into each flip-flop here, right? And we can try to find the Boolean equation for each of these inputs, J and K here, all right? So some of them are a little bit more complex, so they are written down here, but some of them are very much quite simple. Let's take a look at these first inputs here that are very simple, J0 and K0. J0 is represented just by X prime, and as you could see here in this flip-flop 0, we have J being inserted with X prime, obviously, and then K0 being given a high input, I should say. So the value is always high or a 1. For J1 and K1, we could take a look here at this flip-flop number 1, and we could see that J1 is being represented by this AND gate with Q0 and X prime being ANDed together. So simply J1 is equivalent to Q0 and X prime. So, and then similarly, K1 is equal to the state code Q0 plus the input X. And then we can find our equation for our output Z here, and we can see that Z is having Q1, Q0, both are state codes being ANDed together with X prime. And all these have to be true for our output to be equivalent to 1, as we have seen previously here in our Mealy machine that we built. All right, and finally, I want to talk about something that is very useful. You could tell that this circuit here has no connecting wires to any of these levels here. We have our inputs, our state memory, next state logic. Now, all of these are being connected together, but we don't see any wires being attached or anything like that. And that's because we're using what is called tunnels here. And these are so useful because all you have to do is give them a label and a name. And for any label that matches, you could see here's an XP here, and I find an XP here. If there's a value of 1 going here, and we have therefore 0, because after this NOT gate, a 1 turns to a 0. If we have a 0 going into this XP, everything labeled XP will have 0 being inserted in. It's like an invisible wire. Keeps things looking nice, neat, and beautiful, and headache free. So that is everything that I have to say for this. So thank you for watching, and I'll see you in the next video.